Hello, my name is William McKillop, and this is Lab 4 Magnetic Braking with Faraday. So, for the purpose of this lab, we make observations and record data of a magnet falling through a conductive tube of aluminum foil. We model the experiment computationally and compare the measured data and results with the computational predictions. So, a quick look into the results. We had an experimental fall time of 1.304 seconds and a computational fall time of 1.044 seconds. So, for the physical concepts used, we use the Biot-Savart law, Faraday's law, Lenz's law, and Newton's second law. So for the assumptions we made the assumption that the bar magnet is a magnetic dipole, air resistance is negligible, and aluminum foil acts as a non-ferrous conductive tube. So the system is the aluminum foil tube and the bar magnet. The surroundings is everything else, and the initial conditions are treating the bar magnet as a magnetic dipole. As for the procedure, we have assigned the north pole of the magnet with the magnetometer app, drop the magnet into the tube, record the time it takes for the magnet to exit the tube, and repeat this 5 times. So we got our measurements and we found their corresponding values, and we also did 5 trials with the drop times to the right of it, and the average drop time was 1.304 seconds. So goal script model initial conditions. We took our measurements and we put it into the code, and we essentially produced readings based on our data. Coding for tube and bar magnet. So we wrote a function to calculate the magnetic dipole and change in the magnetic flux, and that's what the code shows. So we produced a computational model which showed induced current due to the falling magnet, and to the right of that is a graph of the change in velocity over time. So as for sources of error, timing could have been off when starting the timer and releasing the magnet, which could affect the calculations in the lab. So understanding the simulation. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in the opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? Well, from above, red is counterclockwise, and from below, blue is counterclockwise. What happens to the dynamics of the system when you flip the magnet around? So the direction of B net would be opposite. And how does the total time and tube of your real world system compare to that of your computational system? How might the computational system be made more accurate? So we had the experimental of 1.304 and computation of 1.044, and more trials will mean higher accuracy in this case. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So the start, large velocity due to the force of gravity. During, gravity and magnetic force are equal, and the finished force of gravity is the only force acting on it. So for the first discussion question, we have that the induced current and magnetic force would increase, so therefore the fall time of magnet would take longer. And for the second question, we have the induced current and magnetic force would decrease, and therefore the fall time of the magnet would take less time. Thank you very much.